Hi, I'm Arya Gupta, and I will be presenting the paper Fully Lattice Linear Algorithms. Let me start by describing the structure of a typical distributed systems. In a distributed system, there are several nodes acting to solve one problem, and in all the nodes, there are several guarded actions. In general, we assume that any guard is evaluated in the current state, and to ensure that, we need synchronization. Vijay Garg identified a class of problems which we are going to call lattice linear problems. In these problems, the state form a lattice, and in any suboptimal state, there is at least one node which must execute, which must change its state. We call such nodes forbidden nodes. If a forbidden node does not change its state, then the system may not reach an optimal state. Benefits of lattice linearity. It allows, if the global states form a lattice, then the nodes can be allowed to execute an asynchrony, and the nodes can be allowed to rely on old data of their neighbors. For example, let us look at one of the lattice linear problems, the stable marriage problem. And we have an example where there are 3 men and 3 women. Both have ranked each other according to their preferences, and the induced lattice is as shown in the figure on the left of the slide. Now, given the particular instance on the right, we have that the optimal state is 1, 2, 2, which means that if we start from the infimum, we will be able to reach 1, 2, 2, the optimal state. But if we start from, for example, 2 and 3, and we will not be able to reach 1, 2, 2, because the execution has to take place along the lattice, so it can only go upwards in the lattice. From here, we have an observation that this does not allow, some lattice linear problems do not allow self-stabilization. Now, there are some problems, very interesting problems that are not lattice linear, and they require self-stabilization. One of the problems is minimal dominating set problem. This is an example showing, the figure shows an example of 4 states where the minimal dominating set is being computed on a graph of 2 nodes connected to each other by an edge. Now, if you look at state 4 can transition to state 1, in which case node 2 is not forbidden because it does not change its state. If state 4 transitions to state 2, which is valid, then node 1 is not forbidden. So in this particular problem, it cannot be determined which node is forbidden. And that is what it makes this problem a non-lattice linear problem. And we know that this problem requires self-stabilization. Now, this problem does not allow induction of a lattice naturally, but can we induce a lattice algorithmically? The answer is yes. We introduced, to solve such problems, we introduced eventually lattice linear algorithms, where a subset of the states form multiple lattices, single or multiple lattices. And if the problem requires self-stabilization, then the induced lattice, the supremum of each lattice, is also an optimal state, which means that starting from any state, we will be able to reach an optimal state. This paper is about fully lattice linear algorithms, and in which case all the states take part in forming multiple lattices. And if the problem requires self-stabilization, then it is required that the supremum of every state, supremum of every lattice is an optimal state. This is an example algorithm for minimal dominating set. If we follow this algorithm, and if we consider the graph G4 as shown on the figure on the left, we will be able to see the structure of lattices. The structure of lattices induced is shown on the figure on the right. We can see that the entire state space is partitioned into multiple lattices. All the supremums, the supremum of each lattice is an optimal state. This allows self-stabilization because we can start from any state and it ensures that we reach an optimal state. We have also derived the convergence time for an algorithm that is traversing a lattice of states. So if there are n processes and if there are R variables in each process, the domain size being m1 prime, m2 prime, and so on, the convergence time in such a case is the domain size of every variable minus 1, summation over all the domain sizes minus 1, times the number of nodes. As a result, algorithm 1 is proved to be converging in n moves, which is an improvement over all the algorithms in the literature for the minimal dominating set problem. Algorithm 1 is the first proven lattice linear algorithm for a non-lattice linear problem. Finally, it's still an open question whether fully lattice linear algorithms can be developed for minimal vertex cover and maximal independent set. This concludes my presentation. I'll be happy to answer any questions.